Neve is a high-level systems programming language, but if you want to implement your own operational system intrinsic calls, or you want something like hardware access in a CUDA kernel, or a or a internet network management, an access or an interface to it, then it's better if you get your hands-on into how the foreign function interface or the FFI works. So I will divide this video into two parts. The first part I will just talk about the I'll be straightforward into how to implement a simple lib in FFI, a simple package. And in the second part I will go all through it again and explain how each part works. So I just got a new fresh installation of Neve, and basically what I'm going to do is to pass through the docs pages into this, and I'm going to make the same tutorial into how to make your own data type and some functions. So first of all, I recommend to get the Docker container in Ubuntu, this version of Ubuntu, so you can compile your .so file for many modern Linux distros. And after you installed the Docker container, use Ctrl D to quit it and go to the lib folder, because if you may get some don't if you try to install Neve while Docker is running, you may get some conflicts into file permissions for some stupid reason of Docker. So now create this new folder called package, maybe get into it. This is the Neve. This is always the same Neve directory where it will be installed for many people, and the lib folders where packages get installed. So it will always contain the standard lib as default, and we can copy the make file that is inside the standard lib into this current folder. So after copying it, you notice that my folder already has some files, so please create this .nv and this source folder, and into the source folder you can put these files. After that, let's start the Docker container, and I will jump into the code already. So in the include file, we can put these libraries. This is going to get the standard lib from Neve, and will import the data that is here. So this is a struct. It could be a class, anything that can be cast to a pointer. We can represent in the C++ FFI. So after defining the struct, we will go to the CPP file. And the first thing when we do with a C++ struct or a class is to define its constructor. But the constructor here will have to be left empty because we are not going to use the malloc. We are going to allocate it on the pool. So we are going to separate a new method for the construction of this object. After that, we can make the create function, which allocates the data on the pool, then a print method. So this already allows we to execute your print method into your own created data type after you execute make. So now we can already define some operations like add two placeholders or add a placeholder to an int. Then we can save the file first and use make again. And this will give us the access to the operator overloads. So we can define new methods already, new operations, the data file operation, and the file also needs the cleanup. This everything that's data type will need this cleanup for the garbage collector. So maybe this code ran without the cleanup, but the garbage collector probably didn't run as well. So at that point, so you will need this cleanup function for C++ data type, otherwise it will crash. And finally, I'm just going to show you how you can use varargs. So this allows to create a function with many arguments. So we pass for the scope structs, an integer argument, and after these last arguments, all the other arguments are going to be expected to be an integer. So I'm not using the placeholder data type here. I just want to show you the vararg kind of function. And this is how this is the vararg function working with literally a varying amount of arguments that we can use. So now I'll get to explain you how everything, how this all works. So although I showed you how to create a data type in C++, I don't recommend you to create data types, but this code in C++, but this code is very useful, so you can basically everything Neve can do in C++, on the FFI, you can do it here. There are some other things like returning arrays or making our data type parallel, but at this point, Neve has a great support for high-level stuff, so I don't recommend you to do data types in low level, but this is important for you to understand the conventions it uses, like everything that starts with a DT and is returned pointer to a high-level function. This will become a data type and will require the create function and the cleanup. So basically, everything here is a pointer. You either return pointers or primary data types like integers or floats to high level, and Neve will apply its second compiler front end just to parse all these C++ codes, and it will automatically link the LLVM. It will automatically provide you the LLVM linking that it needs to run this stuff. So not everything can be inferred. For example, if you would try to pass an array here, it wouldn't really recognize the array because it would be just a pointer to an array type. So you have to define the prototype in higher level. But I will show this in the LLVM video, the LLVM libs video, so how you can make more complex prototypes. But in the end, I don't recommend you to try to use arrays in the C++ FFI or maps. Instead, I recommend you to just make very minimal functions that just give you access to system intrinsics, operational system intrinsics, or like the CUDA kernels. So CUDA kernels, they just basically require some few pointers, and they are not lists of pointers. Kernel just takes pointers directly. So proceeding, basically, how does this compiler identifies what does each function do? Well, it's basically just on the name and name mainly. So when this pointer gets returned, it's the compiler, the lib compiler knows that, okay, there is a placeholder. There is a data type called placeholder. And it needs this create function. That's the function that it executes when the new expression is called. So, and in order to identify methods, we just put the data type name first, and then underline the method name. Also note that even the print returns an int, and that's because every function needs to return something in order to build the Neve map, the Neve utils maps. That's how it identifies some functions exist. And here we can see that there's another function that returns the placeholder, and again, it's a dt placeholder pointer, but this is enough to put to create to represent it as a data type. So basically Neve is running a lot of pointers in high level, but it's hiding it. It's hiding how they work. But you cannot really access the X and Y here from the data, from the placeholder, because this would require LLVM linking as well. But if we create a lot of new data types in C++ and in Neve and in LLVM, then it gets very complex to define LLVM structs to representing all this. So I just rather implement the majority of data types in Neve itself. Currently, I think I vaporized all of the C++ data types except for the arrays and maps. But previously I was trying to represent even tensors, even the CUDA tensors in C++ FFI, but that was a very bad experience. So now that Neve itself allows low-level stuff that simplifies a lot of things, and it's memory managed, so there's not really a reason to use the data types here. But again, this is how you learn how to implement any kind of function in the FFI. So after the how we can define methods, well, I could create a new function just by giving it another kind of name here. But this for this specific function, then I would have to pass the placeholder explicitly. But since it doesn't begin with a data type name, then we can just execute this function print ttt in high level directly. And proceeding, this is operator overload. So basically we can just put the left side expression data type and the right side expression data type followed by the operation name, and then we can represent this just like this, just the sum of just or the addition of two data types. Or we can change the data types. We can add a placeholder to an int, which is this expression here. And if you are curious about the names from the other operations, flashbang again. I regret making such a heavy site, but anyway. You can refer here. This gives you a map of what each high-level operation is named, of how each operation is named in C++. You can even use these names and do the same operation overload in high level itself. You don't need to do the same. I mean, you don't need to only do this in C++. So they share the same conventions. And note that every function begins with externcy. This is to deactivate the name mangling that C++ itself adds to the name of functions. So it like C++ adds some random letters in the names of the functions. I think to avoid ambiguity, something like that. But anyway, we don't need that. We just want to access the functions as they are exactly named. And the same applies to multiply all. This kind of vararg is not exactly from Neve, it's a C++ thing. And other thing that you can notice here is that every function with the unique exception of the cleanup of your data type cleanup, every other function must begin with the scope struct. And this is necessary because the scope struct has the memory pool. It has access to the memory manager, the garbage collector, so you can use intrinsics like the newt for or data type. And it also has the thread ID. We could access it with its code. So my fingers are very bad at typing today. So, but anyway, we could get the thread ID here. If we wanted to give a special treatment based on the parallel state of the code. And you also notice that the include NV file is mandatory, but this is because it's only to make you aware that in this early stage of development that you can mix hybrid, can make hybrid high level and low level functionalities. So like you could create your data type in low level C and then try to implement new operations with new uh, with in your package right here. So you could implement the placeholder sum or addition here. It's a very large function name, but anyway. So basically we could mix your code with high level code. This is how the CUDA framework itself is implemented. Basically the CUDA kernels are called in C, in C++, because I cannot represent it directly in LLVM. Well, maybe I could, but it would need the LLVM MLIR, but I don't want to implement that. I want to make CUDA kernel straight. And then anyway, the rest of the code is completely implemented in Neve itself. So I can take the so I have here I define some of the prototypes. Then here I define some of the functions for the tensor data type, but then it has a LLVM data type implemented in C++, not with the FFI that I showed, but with the LLVM C++ backend code, but it's itself a package as well. So every LLVM code defined here is inside a package. Uh, so I didn't make this exact straight in the compiler. And then we have the let me try to recall where the code is. So see here, and here is the FFI being called to define the CUDA kernels. So this prepares for a CUDA kernel, and then this operation launches another function that's a CUDA kernel, but this other code here is better. It calls the CUDA kernel quite directly. And you can see that I'm using the thread ID here to decide the CUDA string that I want to use for this kernel. But well, that's it for how these functions work. I will still launch videos on how the LLVM packages work themselves, and maybe how to create packages in Neve itself. Well, that's it. Hope you enjoyed and hope Neve gets to be your favorite new language as it is mine.